Alright, welcome back guys. In this video, like I promised, I'm gonna reformulate this problem using the analogy between heat transfer, heat transfer and electric current. Okay, this is current and it's we're gonna talk about electric current. We're not talking about any of the other currents. Anyway, sorry. So let's talk about Ohm's law for a second. For current, we're gonna describe current in most ideal cases. The phenomena of charge flow is usually described using Ohm's law. Okay, Ohm's law. And for the case of heat transfer, conductive heat transfer is described using Fourier's law. Okay, these are the two laws that are used to formulate the problems. Ohm's law. Okay, let's look at the statement of Ohm's law. Most physics textbooks just use V equals IR, V being the potential difference. Let me write this as delta V. So it emphasizes the potential difference is equal to current times resistance. And current is the variable. Current is the transport quantity that you're looking at, that you're interested in, and current is proportional to the voltage, the potential drop divided by the electrical resistance. Okay, so this is a very basic result from a if you've taken college level physics, then you should be this should be a refresher. We're just talking about how the rate of charge flow in an ohmic conductor proportional to the potential difference divided by the electrical resistance. Now, in the case of current, the driving force, what drives current, the driving force is the voltage difference. Let's reverse engineer that for the case of heat transfer. Let me get this schematic a little on the side for now. Okay, so Fourier's law. We know that the driving force, from intuition, we know that the driving force for heat transfer is the change in temperature. According to second law of thermo, heat is gonna flow from region of high temp to low temp. That's one fundamental principle that you should remember. Okay, and let's see if we can derive a result similar to Ohm's law. Let's see if we can get a nice equation like the Ohm's law that we have on the left side. So I'm gonna assume constant conductivity. That's the key assumption. Constant conductivity. Okay, assuming constant conductivity, you're gonna get, okay, let's write down my Q dot. Capital Q dot is the rate of heat transfer, will be proportional to the temperature difference, right? And it's going to be inversely proportional to the thermal resistance. All right, temperature difference, that's not an issue. Thermal resistance, that's something new that we haven't really discussed before. Okay, keep in mind the notation, just to make sure that you guys don't get confused, the notation that I'm using, because different transport phenomena textbooks have notations all over the board. Q dot will represent rate of heat transfer. Okay, whereas lowercase q with this vector sign is going to be my heat flux. All right, this is the notation that I'm using, and you should be careful with the notation you use, and you probably wanna confirm with your professor and the textbook that he's using, and to make sure that everything is consistent. All right, good. Let's all right. So far, let's reverse engineer the thermal resistance. All right, excuse me, thermal resistance. Let's see if we can come up with an expression for that. based on our intuition and based on observation. Okay. All right. Now, intuitively, we know that the thermal resistance is going to be inversely proportional to the thermal conductivity, because the more thermally conductive the material is, the less resistance it's going to pose to heat transfer. That's intuition. Okay, that's a very simple result. We know the thickness, all right, in Cartesian coordinates. Like if we have a thick sheet, heat's like it's gonna impede, it's gonna act more it's gonna add more resistance, more thermal resistance, because it's a bigger barrier, and it's gonna be inversely proportional to the area of that sheet. Note this L right here is the thickness of sheet. Okay, we're talking about flat sheets in Cartesian coordinates right now. We haven't discussed spherical or cylindrical yet, and this is the area of the sheet. We're talking about a flat sheet, okay, like the ones in my double-pane window, double-pane window in the schematic. Okay, using this analogy, let's see what we get using the Ohm's law analogy. Using the Ohm's law analogy, the result that we're gonna get, and this is very popular in most undergraduate level heat transfer textbooks, which I'll refer in the description, and you guys can read for further knowledge. So the rate of heat transfer is going to be equal to the overall temperature drop, okay, overall temperature difference, divided by the summation, okay, the net thermal resistance. Okay, this is the result that we have derived. Okay, and let's talk about the terms for a minute. Delta T is the overall temperature difference. Good. All right, nice, good. All right, and looking at our schematic, I'm gonna copy this down here so that we can now focus our attention back to this problem. Okay, good. Here we have it. Good, very nice. Total thermal resistance. Okay, this, and the denominator term is the net thermal resistance. Now let's apply this analogy. Let's apply the Ohm's law analogy to our double-pane window. Okay, keep in mind, temperature is our driving force. Temperature is what's gonna drive heat transfer. So at x equals 0, we have T out. Then we have the outer glass. Okay, let me just blow it up a little. Let me just, hold on, give me 1 second, sorry. I'm just gonna stretch it out a little. Woo, I love technology, and I'm sure you guys do as well. So, make sure my OCD is happy. All right, good. Okay, so here I'm gonna have, on this end, I'm gonna have my outlet, the temperature of the outside, and on the other end, I'm gonna have the temperature of the inside. Sorry, this one is inside, my bad. In, good. And first, I will encounter my first resistance. Let's use the correct colors. My first conductive resistance. Okay, this is conductive resistance. And then I'm gonna have another conductive resistance due to air. And then I'll have another conductive resistance due to the inner glass. Very good. So this right here is the conductive resistance of of glass, inner glass, outer glass. This is the outer glass. This one right here is the R conductive. I'm just gonna abbreviate that. The thermal conductive resistance of air, the air gap. Good. And finally, this is the conductive resistance due to the inner glass. Good. All right, I'm gonna label these. All right, I have my English here. All right, good. I have my English, but English, I can't play around with so many words. So I'm just gonna call this R1. This one shall be named R2, and finally this one shall be named R3. And my overall heat transfer, okay, my overall heat transfer, let's emphasize that a little, is going to be equal to the total temperature difference, and that's going to be from T out minus T in. Okay, T out minus T in, and that's going to be divided by, let's color code this, shall we? Let's color code this. R1 plus R2 plus R3. And let's see. R1 is going to be equal to the thickness, L, divided by the conductivity of glass times the area of sheet. Okay. R2 is going to be equal to the thickness of the air gap divided by the conductivity of air, the material, multiplied by the area. And in this case, the area is the same. The area is the same in all three domains because we're using Cartesian coordinates and we have a flat sheet. We have a flat window. Okay. Both inner and outer glass have the same area. Okay. Good. And this is going to be L over kGa as well. So if I were to rearrange everything, okay, if I want to complete my solution, if I want to find out how much heat is going to be transferred, then that's just going to be the temperature difference, the overall temperature difference. The overall temperature difference divided by the respective thermal resistances. Okay, all right, very good. So using this result, if you have a similar setup, it doesn't have to be glass, it doesn't have to be air. If you can assume constant conductivity for each domain, this result, this equation right here is going to work. If you're using Cartesian coordinates, first off, you're using Cartesian coordinates, okay, and you're assuming constant conductivity in each domain for each material, constant conductivity for each material, and all the obstructions, all the thermal resistance are in series. All the thermal resistances are in series. Okay, we haven't touched so just like series and parallel circuits in your physics class. Okay, nothing too fancy yet. So this result right here, this equation should work. This equation should help me fix I can now play around. Now I can just play around with the thickness of the outside. Thickness of the outside sheet. I can play around with the thickness of the gap. Okay, I can play around with the thickness of the air gap, and I can play around with the thickness of the inside sheet. And I can also see if I can maybe select different materials with different sets of conductivities to minimize my heat transfer rate. Okay, my problem is I'm trying to minimize heat transfer because it's summer, guys. I'm trying to minimize heat transfer. Why? Summer. All right. So I just did this example symbolically. All right, we didn't do any numerical computations yet. Okay, and once you have this result, you can just put it in Excel, put it in Maple, put it in MATLAB, put it in Python, whichever tool you fancy, and you can just get your answers. You can just play around with your parameters. You can play around. You can now plug in different different temperature values, and yeah. So yeah, guys, this was our journey through the double pane window problem. Okay, don't forget our assumptions: steady state, constant conductivity, no bulk motion, perfect contacts. Okay, and one directional transport. We initially went over the solution using the equations of change. Okay, our equations of change gave us 3 second-order ordinary differential equations, and in order to solve these, we needed 6 boundary conditions. And yeah, you can see right here, these are my integrated equations, and these are my 6 boundary conditions, and I didn't really want to solve them, and I was looking for an easier way out, like I always do. So I used the analogy between heat transfer and current. So basically, Ohm's law is what governs current through ideal resistors, and Fourier's law is what governs conductive heat transfer. Okay, let me emphasize conduction here. Oops, we're strictly talking about heat transfer via conduction, so I'm just going to emphasize that here. Good. All right, for current, the driving force is the potential difference delta V, and for temperature, the driving force is the temperature difference delta T. Second law of thermo, nothing too fancy. And then we arrived at this. We came up with this relationship between thermal resistance and the geometry and the material property. Okay, the material property, the conductivity, and the geometry, the thickness and the area. Good. And then yeah, so this is how we reformulated our problem, and according to this setup, we had three thermal resistances in series. Okay, so we could just add them up, and yeah, our final equation that can give me the rate of heat transfer for any given parameters. Okay, for any given parameters. So yeah, guys, thank you so much for watching.